She's going to speak from Princeton University, and she'll speak on the Hodge-Tate period map for Shimura varieties and Hodge-Tate.
Well, thank you very much. I just want to say it's a great honor to speak at this conference in honor of Michael Harris, and his mathematics has influenced me greatly ever since I was a graduate student. So I want to talk about joint work with Peter Scholze. It's work in progress. So I want to talk about the Hodge-Tate period map for Shimura varieties of Hodge type. And just as motivation, I want to say that this period morphism has proved already important for the study of the p-adic geometry of Shimura varieties and has had applications to the study of p-adic automorphic forms, such as so the construction of Galois representations associated to torsion classes and the cohomology of locally symmetric spaces. And kind of understanding the Hodge-Tate period morphism better can lead to more applications and maybe understanding more about torsion classes. And I guess the other thing I wanted to do was, so this Hodge-Tate period map is supposed to be a p-adic analog of something classical, namely the Borel embedding. So I want to actually spend half my talk reviewing the classical picture, especially since, I guess, in the classical picture, Michael Harris's work features prominently. So I want to talk about that, and I want to try to set it up in such a way that it becomes clear how the p-adic picture is just an analog of the classical picture. So I want to start by just talking about Hodge theory first. So if X over C, or maybe let's say we take X to be defined over a number field. And I should say as motivation, of course, we're interested in Shimura varieties, but for now I'll just take X over E to be a projective smooth variety with some number field E. Then, of course, you choose some embedding of E into C and take X analytic to be the underlying complex analytic space. You can compute the p-adic homology of X analytic with coefficients in Q. And this has a lot of structure. So if you tensor it up to C, there is a Poincaré lemma that gives you a resolution of C in terms of the complex of holomorphic differentials, so the complex version of Poincaré lemma, and that gives you a Hodge decomposition, direct sum, over PQ, HQ, X analytic, with coefficients in the complex of holomorphic P forms. So you have the Poincaré lemma, and that gives you a spectral sequence. And that spectral sequence degenerates, gives you a Hodge filtration, and even that is split. So you get this Hodge decomposition. So this is p-adic homology, but you can also look at the de Rham homology. Oh, here, there's the Hodge decomposition. So the de Rham homology of X is going to be defined over E, and this can also be computed as the hypercohomology of the complex of differentials. So now we have the algebraic de Rham complex here, and we're computing it with respect to the Zariski topology. And so this is equipped because you get a Hodge to de Rham spectral sequence, which gives you a Hodge de Rham filtration on H star de Rham of X. So this is already defined over E. And there's a comparison, so Betty to de Rham comparison isomorphism, which is transcendental. H star X analytic tensored up to some period ring, which in this case ends up just being C with the de Rham cohomology tensored up to C. And of course, like this can't even be defined over R. So for example, for GM, which I know is not projective smooth, your period is going to be 2 pi I. So that's going to give you this isomorphism. But anyway, you have something like this. And the Hodge decomposition on this side and the Hodge de Rham filtration are compatible. Okay, so that's the Hodge filtration here. You can define it as fil P Hn is the direct sum of H PQ P prime Q prime over P prime greater than or equal to P, and it's compatible with the Hodge de Rham filtration here. So all of this will have an analog in the p-adic setting, and I'm writing things out explicitly because in the p-adic setting we're going to have a Hodge de Rham filtration. So instead of working with, say, a projective smooth variety, we're going to work with rigid analytic spaces, or more precisely with adic spaces. But when you're adic spaces, so this will exist also for adic spaces, say if they're defined over so some type of rigid analytic varieties which are defined over some p-adic field. And there's going to be a different filtration on p-adic et al. Cohomology called the Hodge-Tate filtration. So I just want to emphasize that these are different filtrations. All right, so we have this Hodge de Rham, and just to okay, so now I'm going to switch to talking about Shimura varieties. And Shimura varieties, well, roughly you want them to be moduli of Hodge structures, and you want those Hodge structures to have a specific type, and those basically correspond to abelian varieties. So if A over C is an abelian variety, then there's Riemann's classification theorem that tells you that these are roughly the same thing. So they're lattices, and then when you tensor those lattices up to C, they're roughly the same thing as Hodge structures of type -1, 0, 0, -1, where I say that HPQ is of type -P minus Q. All right, so we have this L, and I should say the Hodge de Rham filtration for an abelian variety so it's just a short exact sequence. Sorry. Let me take H1. So this is what the Hodge de Rham filtration looks like for H1. And this is important for kind of defining, say, automorphic vector bundles. So let me move on to talking about Shimura varieties. So Shimura varieties are supposed to be moduli of Hodge structures of this type. So I'm going to take Shimura data, Shimura datum Gx, where G over Q is a reductive group, and X is a conjugacy class of homomorphisms from, so H from the restriction of scalars from C to R of GM into GR. And just as a comment, this is the Tannakian group associated to real Hodge structures. So choosing such a homomorphism basically gives you, endows the category of representations of G with real Hodge structures. All right. So this type of data needs to satisfy certain axioms. So one of the axioms will guarantee that X parameterizes exactly Hodge structures of that type. I don't want to say precisely what the axioms are, but when they are satisfied, X is identified with the Hermitian symmetric with a Hermitian symmetric domain, and namely the one associated to G. So it's identified with G of R mod the connected component of the identity of a maximal compact in G of R. So this is under choosing a fixed point, so choosing a representative, and some torus. So this is going to be a Hermitian symmetric domain. And of course, you can define these symmetric spaces for any reductive group. But the nice thing is that when your pair Gx satisfies certain additional axioms, you actually get a Hermitian symmetric domain, and you can get an algebraic structure, and you can get to Shimura varieties. Okay, so you can make use of algebraic geometry. All right, so let me also assume that Gx is of Hodge type. So I don't need to assume this at this point, but just for simplicity, I mean, ultimately, I'm interested in this for Shimura varieties of Hodge type. So that means there will be, there exists an embedding of Shimura data Gx into some G tilde X tilde, where G tilde and X tilde, so this is a Shimura datum for a symplectic group. So G tilde is GSP of a split symplectic space, so some vector space V equipped with a symplectic form. Okay, and when you have an embedding of Shimura data like this, you get corresponding embeddings on the level of Shimura varieties, and as you saw earlier today, that means that you can look at your Shimura variety for G inside the Siegel moduli space, which is moduli of principally polarized abelian varieties. So that's what you get for the symplectic group. All right, so, and I said it's of Hodge type. There exists such an embedding, but a priori there could be more. I mean, there are clearly more than one embedding. All right, so I want to talk about maybe the Borel embedding first before I go to Shimura varieties. So this character, well, this H determines a Hodge co-character mu which is so co-character from GM into GC. The way you get H is, the way you get mu from H is you base change to C and restrict to the first factor. And this is the Tanakian group for the category of graded vector spaces. So if you have mu, you get a grading. So mu gives you a grading on the category of representations, say complex representations of G, and then you can get a filtration from this grading. This is going to be the descending filtration associated to this grading. And let me just say that when H corresponds to some real Hodge structure, this descending filtration will be the Hodge-de Rham filtration. So when H is some real Hodge structure, this filtration, let me call it fil mu, is the Hodge-de Rham filtration. All right. Given this, we can define, first of all, we can define two parabolic subgroups. I'll call it P mu standard. This is one parabolic, namely, well, okay, so one way to look at it is the stabilizer of this filtration on the category of G representations. Another way to write it is the G in G such that the limit as t goes to 0, adjoint action. So this is choosing some representative mu. The adjoint action of mu of t on G exists. And you can check that these mean the same thing. And you can also define an opposite parabolic subgroup, G, limit as t goes to infinity, adjoint action mu of t, G exists. And this is the stabilizer of the opposite, or I guess complex conjugate filtration. Since we have Hodge symmetry, HPQ, complex conjugate is HQP. And I'll call this fil upper mu, again on the category of representations. All right, and so the idea is that you have an embedding of this Hermitian, of this Hermitian symmetric domain into a flag variety. So you can define a standard flag variety, which is a moduli of filtrations conjugate to fil mu. The Hodge-de Rham filtration. And you can also define a different flag variety, which is going to be a moduli of filtrations conjugate to this opposite filtration. And for now, we're just going to think of them as complex analytic spaces. And I should say you can identify this with G of C mod P mu of C under choosing a representative P mu standard. And this one can be identified with G of C modulo P mu of C. Okay. So then X is a moduli of Hodge structures H. And by just assigning to H mu H, you can define an embedding of X into the standard flag variety. So the Borel embedding and I should say that in the case of modular curves, So that would be, say, when your group is SL2, your Hermitian symmetric domain is just the upper half plane. This is the embedding of the upper half plane in P1 of C. Okay, so H goes to mu H, and say by choosing representatives, you can see that that's basically, so X is G of R mod some modular maximal compact, and this is G of C. So you can show that that's a natural map, and this is holomorphic. And there's also an embedding of X into just a flag variety parameterizing the opposite filtration, but that will be anti-holomorphic. Okay, so from the point of view of studying the complex picture, we want to consider this one, which is holomorphic, and has to do with taking the Hodge structure and looking at the Hodge-Durand filtration. And now I should talk about Shimura varieties. So given some K inside GAF, compact open, so some level, you can define your Shimura variety attached to the Shimura datum GX by the usual double quotient. So X times GAF mod K, and then quotiented out by the diagonal action of G of Q. And a priori, this is just a complex analytic space. And it's a union of connected components, and for each connected component, you can think of X as, well, X is the universal cover of that connected component. So if you're interested in, say, studying modular forms as sections of certain coherent sheaves on Shimura varieties, well, you want to ask how you can define these coherent sheaves. And the idea is you can use this Borel embedding. So these are the automorphic vector bundles. And using this, you can define them, and you can show that they have, they're algebraic. So far, everything is a complex analytic space. But of course, these Shimura varieties and the flag varieties all have models over a reflex field. So this is the field of definition of mu as a conjugacy class. All right. And so, first of all, how would you define automorphic vector bundles? Just over C. So, to define over this Shimura variety, well, first of all, note that you have a functor from representations of P mu standard. So this standard parabolic, well, you actually have an equivalence of categories with G of C equivariant vector bundles on the flag variety. The standard one. And then, using the Borel embedding, you can just restrict to G of R equivariant vector bundles on And then using the fact that X is a universal cover for each connected component, you can descend to automorphic vector bundles on the Shimura variety. And then kind of the issue is in seeing that these are algebraic, and for instance, this X is just a complex analytic space. So it turns out that these automorphic vector bundles also have, so they're all defined over E, the reflex field. So they're algebraic, and they're defined over the reflex field, and have canonical models. And this is due to Harris and Milne. This is so I just want to explain one way of seeing maybe a different way of constructing these automorphic vector bundles in such a way that makes it clear that they're algebraic objects and that they're defined over the reflex field E. And this is going to use the de Rham cohomology of the universal abelian variety over our Shimura variety. And this is going to mirror what happens with the Hodge-Tate period map in the p-adic setting. So just kind of one idea for how to prove this fact about automorphic vector bundles is to, well, let's consider Siegel embedding. So you have to choose one. We're assuming that we're in the Hodge-Tate case. We're choosing a Siegel embedding. That gives you, so this is a moduli space of principally polarized abelian varieties. There's a universal abelian variety. So this gives you an embedding of Shimura varieties, closed embedding. This is just Siegel moduli space has a model over Q. So you tensor it up, you base change it to E. Okay, so you have a closed embedding. And you have a family of abelian varieties living over the space. So you can just restrict to pi, so to your Shimura variety of Hodge type. So restriction gives an abelian variety. Okay, so now I want to consider the vector bundle you get on this Shimura variety by taking the de Rham cohomology of this abelian variety. So I'll call this nu de Rham, and this is R1 pi de Rham. So just the first relative de Rham cohomology of A. This is going to be a vector bundle over the Shimura variety. Okay, so the idea now is to construct an intermediate algebraic object. So somehow, to get your automorphic vector bundles, you start with a representation of this parabolic, and you go to the flag variety. So what we want is an intermediate object between the flag variety and the Shimura variety that has an algebraic structure. And this is something that is due to Milne. It's called the standard principal bundle. It's basically an algebraic G-torsor over your Shimura variety that trivializes your de Rham cohomology. Okay, so let me call this G de Rham. This is a G-torsor over the Shimura variety, parametrizing isomorphisms beta of your de Rham cohomology with some, so maybe choose some mu in the conjugacy class, some representative, then tensored with the structure sheaf. All right, okay, so we want this to be a G-torsor. And a priori, this seems like the most that it can do is GLN torsor for some large n. So the other thing is that having something like this allows you to consider, so how do you cut out your group G inside G tilde using some Hodge tensors? So there exists S alpha, which are tensors, so elements in kind of tensor powers of V and tensored with duals of V. So just tensors finitely many such that G is the stabilizer of these tensors. Okay, so instead of just trivializing the de Rham cohomology, we want to trivialize it in such a way that it somehow matches the tensors. And I guess I told you, so there are some tensors just in V mu. However, V mu can be identified with the p-adic cohomology of your universal abelian variety, so that determines tensors in the local system corresponding to p-adic cohomology. And moreover, these are Hodge tensors, so they will live in degree 0, 0, since they're stabilized by G. And you can look at different realizations. So using the comparison between p-adic and de Rham cohomology, this is the de Rham realization of the p-adic tensors. So these are going to be horizontal sections. So you have to write down the comparison between p-adic and de Rham cohomology in families, and you get that they're horizontal sections of this vector bundle. Okay, so you want to look at isomorphisms, trivializations of de Rham cohomology, which match these Hodge tensors. This is a G-torsor. You can similarly, so this is going to map down to the Shimura variety and should also map down to the flag variety. And it turns out there's a canonical map from this torsor to the flag variety. And that comes from the fact that this G-torsor actually comes equipped with a P structure. So G de Rham has a P mu structure, P mu standard structure. So that means it's obtained from some P mu standard torsor via which I'll call P de Rham, via just natural construction going from whenever you have a map of algebraic groups and you have a torsor for P mu for the first one, you can get a torsor for the second one. So the question is, why does this have a P mu structure? Well, because instead of just asking to parameterize isomorphisms isomorphisms of this with the trivial vector bundle and that preserve Hodge tensors, you can also ask to preserve the Hodge de Rham filtration. So I'll just say that P de Rham is defined as G de Rham plus an extra requirement having to preserve the Hodge de Rham filtration. And that should be the same as this fil mu, the filtration associated to the Hodge co-character mu. Okay, so having something like this naturally gives you, so once you see that G de Rham has a structure as a P de Rham comes from a P de Rham torsor, this gives you a map into this flag variety. And then what Milne does is proves that you can obtain your automorphic vector bundles by pulling back along this map and then descending them along this map. So I guess J and K. Roughly, you pull back and then you descend them to the Shimura variety. And one advantage of doing things this way is that this is naturally, this G Durham, this G-torsor is naturally an algebraic object, and you can show that it's defined over the reflex field E using the same method that was used to show that these Shimura varieties or the flag variety have models over the reflex field, namely using CM points and the theory of complex multiplication. All right, so now I want to switch to talking about the p-adic picture. And yeah, I'm sorry I spent a long time talking about the complex picture, but the idea is that the p-adic picture is exactly the same thing, just using a different parabolic. So so for the p-adic picture, we're going to take C to be the algebraic closure of QP bar and then completed. And instead of working with schemes over the reflex field, we're just going to base change everything to C and then use adic spaces, so which are a certain kind of rigid analytic varieties. So in that case, say if you want to prove theorems about p-adic automorphic forms or mod P classes in the cohomology of Shimura varieties, then it turns out it's really useful to think of these as rigid analytic spaces and even to consider a tower of these. And one reason you'd want to consider tower is that, okay, so let me just say we have our Shimura variety K at some level K, which consists of some tame level and level at P. We can base change it to C, and then there's a functor that turns variety into an adic space. So we're going to take the associated adic space. Okay, and then you might want to consider an inverse tower of these things as your level at P gets smaller and smaller. And one reason you might want to do that is because if you want to think about p-adic automorphic forms, you can think of them as classes in the direct limit of the mod P cohomology of these things. So you can ask, does this tower whose mod P cohomology encodes p-adic automorphic forms have any sort of extra structure? And it turns out it has a structure as a perfectoid space. So this is what Scholze proves in his paper on torsion classes. One of the first results there is that this tower of adic spaces has the structure of a perfectoid space. So I'm going to change my notation slightly. So this is going to be a perfectoid Shimura variety. And what this means is that roughly on topological spaces, you have a homeomorphism between the underlying topological space of this and the topological space of this limit. And on structure sheaves, what you get is a direct limit that then you p-adically complete. So there's a notion of making rigorous what it means for there to be a perfectoid space, which is similar to this type of tower. And the idea is to reinterpret this tower as something where you gradually take p power roots. Okay, so I'll just say there's a perfectoid Shimura variety. So this is going to be over C with this large field. And moreover, okay, so one of the main results is showing that there is such a perfectoid space, but that's proved at the same time as constructing a period morphism. In fact, somehow you can only show that it's perfectoid first over some subsets, and then you use the period morphism to get your perfectoid structure over the whole thing. So, and there is a map of adic spaces, pi Hodge-Tate. I'll call it pi Hodge-Tate prime because a priori what this does is it goes from the perfectoid Shimura variety into so the flag variety associated to some G tilde where you're implicitly taking Gx, a Siegel embedding into G tilde x tilde. Okay, so this is just the flag variety associated to G tilde, base change to C, and then you take the associated adic space. So there is such a map. This has, because we've taken an inverse limit, we've taken this tower, the Hecke action at P on these spaces gives you an action of GQP on this perfectoid Shimura variety. And this has a natural action of G tilde QP. G embeds into G tilde. So this is equivariant for the GQP action. And it's also equivariant for, well, there's a Hecke action away from P, which is not seen at the level of the flag variety. So action considered as trivial on the flag variety. So somehow this gives you a source of lots of Hecke invariant sections of, say, automorphic vector bundles here, which you could just, say, pull back from finite level. So trivial on the flag variety. So what I want to talk about for the rest of this hour is, well, the way this is constructed is basically by considering a embedding into a Siegel moduli space, and then just constructing the Hodge-Tate period map for the Siegel moduli space at infinite level for this perfectoid version. And there, you just have a moduli of abelian varieties. And I can tell you what happens on points. So if A over C is an abelian variety, then pi Hodge-Tate, well, this defines a point of Siegel moduli space, of the perfectoid Siegel moduli space, and pi Hodge-Tate gives you a trivialization of the Tate module of this abelian variety, which on the dual side will give you a trivialization, so say dimension G, will give you a trivialization of the étale cohomology. And then this étale cohomology, after you tensor it with C, has a filtration called the Hodge-Tate filtration. Which looks very similar to the Hodge-Durham filtration on Durham cohomology, but actually the graded pieces show up in a different order. So that's part like why I wrote this Durham filtration. So your first piece will be H1 of A, OA, 0 to H0, A, omega 1, A, and with a Tate twist to 0. So if you trivialize this, you can just look at parameterize subspaces of a 2G dimensional C vector space, which are totally isotropic. That's kind of the condition for Siegel moduli space, and that just defines your Hodge-Tate period map at least on points, for your Ziegel moduli variety. And the natural question is, when you have a Shimura variety, just of Hodge type, can you show that, can you prove something stronger? Can you prove that this Hodge-Tate period map actually factors through the flag variety associated to G, and can you show that it's independent of your choice of symplectic embedding? So let me just state the theorem, and then I'll explain how basically the same ideas used for the complex picture apply. So this is with Scholze. There exists a GQP equivariant map of adic spaces pi Hodge-Tate from the perfectoid Shimura variety into the flag variety for G. So this is just, again, defined over some reflex field. This is the flag variety parametrizing kind of the complex conjugate filtration to the de Rham one. So there is such a map, and this is independent of the choice of symplectic embedding. And the second thing is that you can ask about automorphic vector bundles, because in the complex case, you can construct your automorphic vector bundles as algebraic objects over the reflex field by pulling them back from the flag variety. So this is the second point. Which is, well, I'll state it as there is an isomorphism of tensor functors given by the following commutative diagram. So you can look at, so one thing is that you see you have different parabolics in the complex case and in the p-adic case. So what they have in common is a levy. So if you choose a representative mu of this class of Hodge co-characters, M mu is the centralizer of that. This is the common levy for both p mu and p mu standard. And maybe you can't compare things, so automorphic vector bundles that are induced from genuine representations of p mu, but maybe you can kind of compare the ones that come by inflation from representations of the levy. So you can look at representations of M mu, you can inflate them to p mu, and then that will give you GQP equivariant vector bundles. On the flag variety for G, it's adic 1, or you can, and then, sorry, I should say, then if you have this Hodge-Tate period map, you can pull them back along the Hodge-Tate period map and get GQP equivariant vector bundles on your perfectoid Shimura variety. So that's one way to get to GQP equivariant vector bundles, and another way is by going through automorphic vector bundles at finite level. So at finite level, but you have to tensor them with the completed structure sheaf. And then you can just pull back from finite level. And the idea is that this diagram commutes. And so you can construct your automorphic vector bundles either way. And the reason why you have to basically, so maybe I'll explain what this is, but just this has to do with the fact that in order to get a Hodge-Tate filtration, you don't get it on the étale cohomology, but you have to tensor with this completion of the algebraic closure of QP. And it turns out you need to do something similar if you want to talk about vector bundles and make this work in families. Yes. Yes. Thank you. Sorry. Yes.
The completed thing is sort of the completion has already happened by Jordan's KP, so it's an intermediate step between the tensor with OHAT is something intermediate between finite level and the perfectoid universe.
Yes. Yes. Okay. So if you, the comment was that you can say that this tensor with the completed structure sheaf is implicit in the pullback from finite level to the perfectoid, Shimura variety. And so I just want to say there are two ideas that go into this. So one has to do with how this Hodge-Tate filtration is defined. So just as you saw, you had this Hodge-de Rham filtration that was related to the, sorry? Yes. This compatible with pi Hodge-Tate prime. And for the compatibility, the idea is to kind of just construct something functorial and then get that automatically. But so one idea is to use the comparison between Betty and de Rham cohomology, so the p-adic comparison, p-adic de Rham comparison in families, as proved by Scholze. So this is 4 adic spaces that are defined over a finite extension of QP. So see how this induces the Hodge-Tate filtration. And the second idea is very similar to what happened in the complex picture. So I'll just say, so if mu p is the p-adic étale cohomology of your abelian variety over the just over the adic space. So if you have something like this, basically construct torsors. Just say m mu, p mu, g torsors, trivializing this local system. Well, really trivializing mu p tensored with OS completed. Okay, so maybe in the remaining time, I'll just say a little bit more about how you would do one. So for one, the idea is, first of all, there is a basic comparison between étale cohomology and coherent cohomology that's due to Scholze, which is if you take the local system given by étale cohomology and you tensor with the completed structure sheaf, then this is isomorphic to R1 pi lower star of OA hat. So all of these, I guess, whenever X is some adic space, you can define OX hat, a completed structure sheaf, as a sheaf on the pro-étale site of X. Okay, so there's a basic comparison that comes from a comparison between étale cohomology and coherent cohomology mod P, devisage, inverting P, and forgetting an almost. So there's something like this. And then you can see the Hodge-Tate filtration, or at least the first step in the Hodge-Tate filtration, even in families. So in the relative Hodge-Tate filtration. As R1 pi lower star OA tensored over OSK with the completed structure sheaf and the natural map from this into here, which turns out to be an injection. And in general, for adic spaces, say defined over a finite extension of QP, you have more general Hodge-Tate filtration, and that comes basically from looking at étale cohomology as the cohomology of this completed structure sheaf, and then comparing it to the complex of differentials. And that has to do with basically looking at this on the pro-étale site and then descending it on the étale site and showing that there you end up with somehow the complex of differentials showing up as higher push forwards of this structure sheaf on the étale site. Okay, so that's one way of seeing the Hodge-Tate filtration, but it's not so helpful if you want to, say, relate things to de Rham cohomology. So I claim that there's another way to see the Hodge-Tate filtration, which is by looking at, so another way is the p-adic de Rham comparison. So just as the comparison between Betty and de Rham cohomology, you had to tensor with some period ring. So now we want something in families. And we also are in the p-adic case, so we have to tensor with a really big ring. And so for that, we're going to need to consider things like B de Rham plus, which is the relative period sheaf. So if you were to, so B de Rham plus A, this is a relative period sheaf on A pro étale. And it's something that showed up in Peter's talk yesterday. It was this, over COC points, it's just Fontaine's B de Rham ring. You can define a relative version of this by, I'll just say in words, you have something like, you have the structure sheaf of A, you reduce it mod P, you perfect it, and then you take Witt vectors. So maybe I'll just say Witt vectors of OA tilt plus. So it's naturally it's something that's naturally defined on, say, affinoid perfectoids, or, but you can define it on adic spaces in this case. So you take Witt vectors, you invert P, and then you have to complete, p-adically complete at the kernel of theta, where theta is the map from the Witt vectors of this perfected mod P structure sheaf. This gives you a natural map into OA plus. Okay, so you can construct a relative period sheaf, and this comes with a filtration that's just like the filtration on B de Rham, and in particular, if you take, so this has a filtration and GER 0 B de Rham. Okay, so this is the plus version, is just this completed structure sheaf. So you can see your completed structure sheaf. The filtration comes from the kernel of this map theta. Okay, so roughly the idea is you want to, instead of tensor your p-adic étale cohomology with this, you want to tensor it with the B de Rham, this relative period sheaf, and maybe even something more, actually, because you want to do it in families. So you have to consider some OB de Rham, which is a structural period sheaf. So it's just, I guess, as an additional structure, it has an action of OA. It's a coherent sheaf. Structural period sheaf. And then the idea is you can write down the p-adic de Rham comparison as R1 pi lower star of b de Rham plus on A, which sees the p-adic et al. Cohomology and tensored with this relative period sheaf on SK, this structural sheaf. So this is kind of a mixture of p-adic comparison isomorphisms and looking at the, say, an analog of the Riemann-Hilbert correspondence. But something like this is isomorphic to R1 pi de Rham lower star OA, and then tensor over OSK with OB de Rham SK. So roughly, you have the p-adic et al. Cohomology on this side, you have the de Rham cohomology on this side, and you tensor them with this structural period sheaf, and then you get an isomorphism, and this isomorphism is compatible with filtration and with connection. So all of these have the usual structures. Okay. And sorry, I'll end very soon, just a couple of minutes. So it's compatible with filtration and connection. And so you can recover your R1 pi lower star OA hat as the GR0 nabla equals 0 of the left-hand side of this comparison isomorphism. Okay, now the point is that this has a Hodge-de Rham filtration. And this Hodge-de Rham filtration will define a different lattice. So let me take M to be R1 pi star B de Rham plus A. This is B de Rham plus local system on SK, whose zeroth graded piece is this p-adic et al. Cohomology tensor with the completed structure sheaf. So you have something like this. This is basically the p-adic et al. Cohomology. And you also have M0, which is the local system corresponding to de Rham cohomology. Pi de Rham OA and tensored. So we kind of don't want this to be necessarily compatible with filtration. We just want to use the Riemann-Hilbert correspondence, well, a version of it, to define. So this is a local system corresponding to de Rham cohomology. And just like in yesterday's talk, these are both B de Rham plus local systems in the same B de Rham local system. So they're somehow both lattices. Well, if you look at points, they're both lattices in the same space, in the same B de Rham module. And because of that, basically, you have a Hodge-de Rham filtration here. Just on the de Rham cohomology, and you have a Hodge-Tate filtration on p-adic et al. Cohomology. And the point is that under this comparison isomorphism, they're related. So what's happening is the B de Rham plus structure here induces a filtration on the zeroth graded piece of this M, which is the Hodge-Tate filtration. And conversely, the B de Rham plus structure here induces the Hodge-de Rham filtration on the de Rham cohomology. So these two lattices give you the Hodge, well, show you the relationship between the Hodge-Tate and the Hodge-de Rham filtration. And I've talked about how to prove part one, and now just to say what you need to do in part two is basically check that your Hodge tensors preserve your Hodge-Tate filtration. And the idea is that your de Rham tensors preserve your Hodge-de Rham filtration, and that under this p-adic comparison isomorphism, de Rham realizations and p-adic realizations of Hodge tensors are matched, and that's resulted due to Blasius for number fields, and it's Since you have horizontal sections, you extend it over each component of your Shimura variety. So for part 2, you match de Rham and p-adic tensors. And I'll finish here. Sorry for going over time.